Hi, my name is Hyan Huang, and I'm going to be talking about Lab 3, which is about magnetic fields of a bar magnet. First, I'm going to introduce the lab. So the purpose of this lab was to measure the distance dependence of the magnetic field due to a small bar magnet and to compare these measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the Biot-Savart law. And we were able to do this by measuring the distance from the bar magnet to the phone's magnetometer sensor in which certain magnetic field magnitudes were created. And fundamental physics principles we used for the Biot-Savart law and the formula for distance dependence. And so with the distances that we measured, we found the magnetic fields, and then we plugged this into this formula to find n, which is our distance dependence. So my findings were that the distance dependence was negative 2.9419, the magnitude of magnetic moment was 9.044 times 10 to the negative 7, and the experimental B at 45 degrees was 1.323 times 10 to the negative 5, negative 1.80 times 10 to the negative 5, and negative 0.00045. And the B at 45 degrees from our computational model was 9.98788 times 10 to the negative 6, 2.99636 times 10 to the negative 5, and 0. I'm going to be briefly going through the lab procedure. So first, I placed my smartphone flat on the table and rotated slowly until X component of the magnetometer app was 0. And I did this to compensate for the Earth's magnetic field. And by lining my phone up to the Earth's magnetic field, I could make sure that the magnetic field of the bar magnet was orthogonal, which meant that they were separate from, so I could measure them because they're separate from each other. And then I aligned my meter stick along the bottom edge of my smartphone so that it runs east to west, and I placed my magnet at the end of the ruler so that its axis is lined east to west. I then located the magnetometer chip on my smartphone and recorded distances from magnet to the sensor in which the magnetic field's magnitude and the X components were 20, 70, 120, and 220. And then I found the distance perpendicular to the magnet in which the net magnitude field has a magnitude of 100. And then I added a second ruler perpendicular to this first ruler and aligned it with my phone sensor and moved my phone up to the second ruler so that it was a distance perpendicular from the horizontal ruler. And with both of these perpendicular distances, I could find just the distance by using Pythagorean theorem. And so this was the data that I collected. So this is the distances that I was talking about that I measured. And this is the magnetic field in the X component, the magnitude of the magnetic field. And then here it just averaged my R's and my BX's and then found the ln of these two and plotted the points. And here you can see that ln R is my X and ln BX is my Y. And this formula says that ln of the magnitude of Bx is equal to ln K plus n ln R. So this means that n is my slope of this graph, and so my n, or my distance dependence, is negative 2.9419. I also found the magnetic field 45 degrees off axis, and that was 1.323 times 10 to the negative 5, negative 1.80 times 10 to the negative 5, and negative 0.00045. And you can see the data and how I got this here. I then calculated the magnitude of magnetic moment with the data that I collected. And so here I plugged in mu naught over 4 pi times 2 mu over r cubed for my b bar. But I said that r is 1, so then that gives me k equals mu naught over 4 pi times 2 pi. And then I plugged in the ln k that I got before in my graph, and that was negative 13.916. And after calculating that, I got 4.522 for my magnitude of magnetic moment. So now I'm going to be talking about my computational model. So here you can see I created a function for the magnetic field of the dipole, and then I created arrows for the magnetic field on axis, and then I also created arrows for the magnetic fields perpendicular to the axis. And I also found the magnetic field for when I was using an observation location that was 45 degrees from the axis. And here you can see all the things that I just talked about. The orange arrows were my magnetic fields on axis, and my blue arrows are my magnetic fields perpendicular to the axis, and my purple arrow right here is my magnetic field at 45 degrees from the axis. So what if I hadn't oriented my experiment to compensate for magnetic north, and I instead laid out my meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? So as I was talking about earlier, the reason why that we made sure to line the phone up to magnetic north was to make sure that the magnetic field of the bar magnet was orthogonal, and that means that I could use the that means the magnetic field for the Earth at the x component is 0, so I could just use the x component to find the magnetic field for my bar magnet. And if I hadn't compensated for that, that would have made my results very inaccurate, because then I don't know what portion of the net electric or net magnetic field is from the Earth's magnetic field and what part of it is from the magnetic field of the magnet. And if I were to stick two identical magnets together and then run the experiment again, my magnetic field would have been much greater, and that would cause the distances that I needed for the x component magnitudes of the magnetic field to be like 20, 70, and etc. to be much smaller. And that's it. Thank you for listening.